Okay, so here we're going to be doing standard 1.3, which is on normalization and orthogonality. We're going to be doing problem 1.2 from McIntyre. And it tells us to consider the three following quantum states. We have psi 1 equal to 1 over root 3 plus I root 2 over root 3 minus, psi 2 equal to 1 over root 5 plus minus 2 over root 5 minus, and psi 3 equal to 1 over root 2 plus e to the I pi over 4 over root 2 minus. And before going on to part A of this question, we're just going to do a quick mental check that these states are normalized. And to do that, we're just going to look at the modulus squared of the corresponding coefficients of the basis vectors and add them together and see if they're 1 or not. So here we have 1/3 plus 2/3, which is 1, 1/5 plus 4/5, which is 1. For the last one, we have to do a quick note that this quantity here is a primitive eighth root of unity, therefore has modulus 1. So once again, we have 1/2 plus 1/2, which is 1. So each of these are normalized, and now we can go on safely to the next part of it, which is part A of the question. And it states that for each of the psi i's above, find the normalized vector phi I that is orthogonal to it. And we actually know the answer to this already if we do some clever thinking. And the way we know that is that since we only have two basis vectors, this is a two-dimensional system, we have basically we're just going to want to flip the coefficients on the two basis vectors up to some sign change. So one of these may have a sign flip, especially if two complex values. We can do a quick check here to see if one of these works. And for the first one, when we take, basically we're going to take this and we're going to take the corresponding bra, which means we take the Hermitian conjugate of this state. And when we multiply these together, we're going to have a 1/3 times the negative of this, and a 1/3 times the positive of this. And when we add those together, they're going to sum to 0, which shows that these two states are orthogonal. And similarly, things are going to happen here up to some sign change. For example, this one we're going to have a coefficient swap. However, this is going to become a plus. And now that we know that, we can go on safely to the next part and check our work. So if we get something different, we know we made a mathematical mistake. So let's quickly jump into these three. So I'm going to start with doing psi 1 out fully, and then just note how the following two follow and do a little less of the explanation. So starting with psi 1, we're going to take the inner product with some arbitrary state we're trying to find, phi 1 prime. And the reason we have a prime here is because the state may not be normalized. Phi 1 we want to be the normalized vector that's orthogonal, and it's very unlikely that we're going to correctly guess the corresponding scaling to make it normalized. So we'll just adjust for that later and call this one phi 1 prime. So we let phi 1 prime be equal to a1 plus a2 minus, and we multiply that by the corresponding state psi 1, and we get a1 over root 3 plus a2 times root 2 all over root 3. And this shows us that a1 is equal to negative I root 2 times a2. And here we can choose a1 and a2 to be anything we want, granted that it satisfies the equation. So we're just going to make it simple and choose a2 equal to 1, and a1 will correspondingly be equal to negative I times root 2. This gives us the unnormalized state vector of phi 1 prime equal to I root 2 plus 1 times minus. To get the desired orthonormal vector, we have to normalize. To do this, we take the inner product of phi 1 prime with itself, set it equal to 1, and find the corresponding normalization constant a. And we've done this before, so I'm not going to go through it exactly, but it leaves us with a is equal to 1 over root 3. And this gives us the corresponding orthonormal vector of phi 1 equal to I root 2 over root 3 plus 1 over root 3 minus, which is exactly what we expected from our above observation. And now going through the following two, we can do a similar process for psi 2 and psi 3. And here we just find what b2 and b1 have to be for our coefficients, find the normalization constant capital B, and we get the corresponding orthonormal vector of phi 2 equal to 2 over root 5 plus 1 over root 5 minus, which is once again what we expected from our above observation. And finally, do this for psi 3 and go through the same process, and we're left with the corresponding orthonormal vector of phi 3 equal to e over e to the I pi over 4 over root 2 plus 1 over root 2 minus. And once again, this is what we expected. So part B of this question is a little different, and it wants us to calculate the inner products of each of these three psi vectors. And so instead of doing all of these out, because there's a lot of combinations, we want to try and reduce some of the work we have to do. And to do that, we can first note that psi I, inner product with psi I, is equal to 1 for every I, because each of these state vectors are normalized, which is why we checked this above. This reduces some of the work we had to do here. But for the other cases, we're going to do them out. So for psi 1, inner product with psi 2, we have 1 over root 3 times positive bra minus I root 2 over root 3 minus bra times the corresponding psi 2 from above, which is 1 over root 5 plus minus 2 over root 5 minus. And when we go through and combine all our terms in one fraction, we get 1 over 2 root 2I all over root 15, which is the corresponding inner product value we wanted. And now similarly, we can go through the next two. And for this one, we're going to have to do a little complex analysis trick in the middle. When we take our inner product and do the corresponding multiplication here, we're going to have to combine this complex value with this complex value, because one's represented with an exponential and the other isn't. And to do that, we're going to note that negative I is equal to e to the I quantity 3 pi over 2. And now when we do that, we have two exponentials where we can multiply and add their exponents. And to do that, we get 1 plus root 2 times e to the I quantity 7 pi over 4 all over root 6. We can do one more simplification, which isn't completely necessary, but I chose to do it anyways. And that's noting that 7 pi over 4 is equal to negative pi over 4. And once we have the negative and the exponent, we can bring it down for equivalence for complex values. So that tells us that the inner product is equal to 1 minus root 2 times e to the I pi over 4 all over root 6. And finally, we can do psi 2 inner product with psi 3. Goes through the math, and we get that the inner product is equal to 1 plus 2 e to the I pi over 4 all over root 10. And now officially we do have 3 left, which is flipping the sides of the two, psi I and psi j. But we're not actually going to do that because we can note this one nice fact. And that's lastly, it should be noted that psi j inner product with psi I is equal to the complex conjugate of psi I inner product with psi j. So now that we've already done these three, we get the other three for free by just taking the corresponding complex conjugate. And that gives us these three values. And now that we have that, we just basically flip the signs on the summands in the middle, and that'll give us it. So thank you, and that's it.